All right, guys, I am here and a little bit off center as I'm going to share with you how to solve these problems that I gave you for gas stoichiometry. Looking at the first question here, we're asked how many grams of the ammonium chloride will we develop? First things first, the reaction is balanced 1, 1, and 1 like that, so crucial to have the balanced reaction. Now, these are both gases, so we need to figure out which one will produce less moles of the ammonium chloride. So to do that, I simply used, for the ammonia here, PV equals nRT, where the pressure is 1.02 atmospheres, times the volume of 4.21 liters is equal to the N, which is the X I'm trying to find, times R, which is 0.0821 liters times atmospheres, over moles times Kelvin, times the T, which is 300 Kelvin. And I got for that, I got an N here equal to 0.174, and that's for the ammonia. 0.174 moles of ammonia. And then I repeated that for the hydrochloric acid here. So PV equals nRT. And again, we can do this because they're gases. So 0.988 ATM times the volume of 5.35 liters, nice work, is equal to N times 0.0821 liters times atmospheres over moles times Kelvin times the Kelvin, which is 299 K. And I got an N here for number of moles of 0.215. Okay, almost everybody got this question correct. And one of the things that helped people get it correct was the fact that this is a 1-to-1 ratio. We still have to figure out which one makes fewer moles of the ammonium chloride. Because it's 1-to-1, you automatically, most of us picked the smallest one, but a lot of people did not bother to do a mole coefficient step on this. So that step looks like this, 0.174 moles of ammonia. In the balanced reaction here, we can produce 1 mole of the ammonium chloride for every 1 mole of ammonia. So that will not change appreciably. It's going to be 0.174 moles of ammonium chloride. And then here, 0.215. Now, obviously, it's not going to change, but I feel like I need to show this step. So this was moles of the hydrochloric. And on the top here, 1 mole of the ammonium chloride. And on the bottom, 1 mole of hydrochloric. So even if you omitted this step, you still got the right answer because it was a 1-to-1 ratio. So 0.215 here moles of ammonium chloride. We're going to omit this one because it is the larger. So I'm simply going to take this now and I'm going to multiply it by the formula weight of ammonium chloride, which is, I used 53.45 grams of ammonium chloride. And that's over 1 mole. And that got me my answer, which is 9.30 grams of ammonium chloride. Hey, go back. Go back again. Oh. NH4Cl. And that was the correct answer. Okay, let's go to the second question here, which is 2 solutions. Now, these are both liquids given, and they have molarities. And we're asked for the conditions, how much of the CO2 here will be developed, and that is in volume liters. So that means we're going to have to end with the ideal gas law. So what I then do is this. I make sure that I have the balanced reaction. Now, I gave you the balanced reaction. Maybe that was a problem because it's a 2-to-1 ratio between the two. And this was where things went awry. So, uh, come back. Okay. So what we then do is this. We take the 50 milliliters as 0.050 liters times its molarity because it is a solution, and that's so 1.0 moles of hydrochloric for every 1 liter. And I'm going to go from there right into the mole coefficient step, and this is what a lot of people did not do. And that's so on the top here, 1 mole of carbon dioxide for every 2 moles of hydrochloric that we start the reaction with. And by doing that, I got 0.025 moles of CO2. I then repeated the exercise with the sodium carbonate, so 0.045 liters here. Again, I have to work in liters. It's a solution, and it is 0.75 moles of sodium carbonate per 1 liter. And then we go into our mole coefficient step, which is 1 mole of carbon dioxide for every 1 mole of sodium carbonate. And we get this answer of 0.038 moles of CO2, which is larger, and I'm not going to use. A lot of you use that because you did not do a mole coefficient step for either thing now. So what I now have is N down here equal to 0.025 moles, and I'm going to solve for volume. So PV equals N times R times T. So 132 kilopascals times the volume, which is the X we're trying to find, is equal to 0.025 moles, times R, which for kilopascals is 8.31 liters times kilopascals, over moles times Kelvin, times T, which is 300 Kelvin. When solved for volume, volume equals 0.47. And I'm just going to do this in 2 significant figures because of the molarities. So 0.47 liters is, and that's CO2, and that is my final answer. And that's what I'm going to stick to. So this one was pretty well done, but most people failed in this area up here, and I'm going to highlight it. And that in some Penrich green, you forgot to do this. You successfully went to moles of both things, but you forgot this. So don't forget the mole coefficient step. If you got that done, then you were in good shape. All right, that is a tutorial on the homework. I'm also going to attach a copy of the homework that is a visual for you to see as well. Hope things are going well, and that as we go into Graham's Law, and I will see you. Take care, guys. Bye-bye.